Okay, so thanks a lot for organizing this workshop. So let's go back to geodynamics now. I will talk about mantle plumes, geodynamics, and I will show you some results from some numerical experiments. So here. So you all have this, this idea about mantle plumes that is like quite theoretical, and that was developed first by Morgan and Wilson. Actually, a big quest of seismologists has been, since this theory was put out, was to find evidence of these conduits, these plume conduits. And so they tried to find some evidence. So you can see this image. You already saw this earlier. And now we get to more complex shapes. So you have these clusters of plumes, maybe, or thermochemical plumes. We even have trees of plumes. From this, I wanted to say that actually these are just instantaneous pictures of what we see at present day in the mantle, and they don't give us any direct information about the evolution of these structures that we can image now. So the big quest now is what led to these structures that we can image now. And so we have to go back in time and try to understand the past dynamics of such structures that we can image now. And so to do so, we need the help of modelers. So here you have actually a picture of a female scientist, which was drawn on a famous hotspot that Dominique talked about, which is Hawaii. And you could imagine that you replace this nice lady by Anne Davey, for example, and that's what you get. So, for example, you can have nice thermal plumes in laboratory experiments, and you can see the evolution through time of these structures. And you can also replace this nice scientist by another kind of scientists, like Cynthia, for example. And so you can go for hardcore coding and get this thermal evolution of a mantle plume as well. And so from these, you can try to compare what you get in terms of dynamics, what you see in those models, to some geological evidence, so seismic tomography, but also geophysical data like the topography or the geoid, or even geochemical data. But there's something that's still kind of missing in all what I show, is that actually mantle plumes are not alone in the mantle, and they are actually interacting with many different structures. So maybe we need to take that into account in order to understand the dynamics of what we see here in tomographic images. So that's what I propose to talk about in this presentation. So I propose here to use these kind of models because, so thanks to Paul and his nice code, we are now able to model fully dynamically mantle plumes in interaction with both mantle convection and plate-like behavior. And so in these models, which are very imperfect in many ways, we can put a number of parameters that you can see here. And one of the interesting thing is that you can have plate-like tectonics. You can characterize it, quantify it with Earth-like surface topography, heat flow, and velocities. And also, you can have mantle plumes that interact with all those structures that you can see here. And since we use models, we can actually do whatever we want and use multiple models. So here you see 3 models. So there's one stagnant lead model. So that means that there's no active plate tectonics at the surface. You see a model with plate tectonics with thermal plumes only inside. And here, what you see here at the bottom of the mantle in this model are thermochemical pipes. And so we can use these three models in order to understand the general behavior of mantle plumes within their environment. And so the first thing we can do is try to quantify their behavior and see if they actually look like what we know from mantle plumes on Earth. So here you have some characteristics that we can infer from observations, from surface observations for Earth mantle plumes. And here you have 4 graphs which show how we can compare model mantle plumes with reality. So actually there's a gray bar that should be here, but that doesn't show up. But actually you have to trust me then. The histograms here show the physical characteristics of model plumes. For example, the radius, the thermal excess, the heat flux, and the buoyancy flux. And they are kind of comparable with the range of observations that we have on Earth. And then from these models, we can also characterize a number of behavior, of characteristics, like the lifetime of mantle plumes. And so, for example, you see that whereas in stagnant lead models, mantle plumes can last forever, well, nearly forever. It depends on the duration of the model, of course. In models with plate-like behavior, the lifetime of plumes is limited to a couple of 100 million years. Something else that we can do is try to track the plumes and their positions through time and try to see if they are mobile or immobile through time. So here you see that if you have a stagnant lead as well, most of the plumes are kind of static, whereas motions can be found in models where we have interactions between plumes and either plate tectonics or other heterogeneities in the mantle. And then what we can do as well is to try to look at their shape, to try to characterize them in these models. So here you can see again that in stagnant lead model, plumes are quite vertical, whereas when they interact with their environment, and if the environment is quite heterogeneous, then you can see limited tilting or more pronounced tilt if you have thermochemical piles. And so from all of these observations, we can actually build a number of different categories of mantle plumes behavior depending on their environment. And so you can see that, for example, we can have fixed plumes that are located at saddle point of the lower mantle convection. But some of the plumes, like these ones, for example, interact with slabs and can be pushed away by slabs. And this time sequence shows you actually this. And so in this case, so you see that this red dot shows the actual initial position of this plume, and you have a kind of organization of the flow in the lower mantle of this model, which means that which actually shows that the slab which is entering the lower mantle here is actually pushing the plume aside. So actually the picture of what we have in those models from mantle plumes can be quite complex and quite different from like the single plume modeling that I showed you before. And here you can see, for example, a thermal plume, a thermal convection model, where you can see those very complex structures of mantle plumes interacting with, for example, slab remnants, and it's kind of quite complex. You can agree on that. So just to be clear, here I'm not saying that this can explain what Karin has shown earlier, but it's just to be aware that there's some complexity that can arise if we just look at plumes interacting within their environment. So in the next part of the talk, I will actually focus on some interactions, some specific interactions that can arise from these models. So if we stay on this interaction between plumes and slabs, something that can occur, I hope that you can actually see this time sequence. So it goes from here to here. So here you have actually a slab which is colored in shades of green, and you have mantle plumes. And so initially this mantle plume it was kind of straight, so it was the Morgan kind of plume. And then since you have this slab which is stagnating at the transition zone, it kind of beheads the mantle plume, and since material is kind of flowing up and wants to go upwards, this mantle plume just creates two heads that can then evolve, and if the slab goes down or goes away, you can reconstruct a single plume conduit. And actually from that, you can track the hotspot track that you would see at the surface from this model. And something that you can interestingly see is that you can create parallel hotspot chains that are actually not separated by a large distance. And together with some tomographic images and some geochemical data, we kind of argued that this could be an analog, a model analog of what we can see in the Coral Sea here. So you have Australia here, the Coral Sea, and you have like a kind of double hotspot track, like parallel hotspot chains that are separated by less than 1,000 kilometers and that are located here. So here I talked about interactions within the mantle, but there are also interactions between mantle plumes and the surface. And here you have some examples of what we can see in the models of interaction between mantle plumes. So you can see the top of the mantle plumes here in yellow, and we have like a top view on the models. And so you can see there are interactions with the plate boundaries. So you have ridges in red here, or slabs, trenches in blue. And so you can see that you can have stable plume ridge interactions. You can have plume-induced ridge jumps from one position to another position of the ridge. You can have the creation of a new ridge here, a kind of a plume-induced ridge propagation, or you can have plume-ridge trench interactions that can become very, very complex. And so here it's another example of what we can see. So if you focus on this plume, which has just arisen from the bottom of the mantle, you can see that it just created two slabs that are then interacting with other plumes in the model before reaching a continent. So I will spend the last part of the talk trying to decompose what we see here in this movie. So if we take some snapshots of this movie, we can see that, so this is the topography field. You can see that, indeed, when the plume arrives at the surface, it induces the initiation of two subduction zones. One of them is just dying, but the other one is propagating towards a continent. And then you have a progressive deactivation of this subduction once it reaches the margins of the continent. And so in this time sequence, you can also already see that you can create multiple ridges and small plates when you create these small subductions. You can, those subductions, which are initially very small, can then propagate over large distances, and you can have very long segments of subductions. and you have an age progression of the deactivation of the subduction along the continental margin. So if we look at what happens in the interior at the same time, what we can see is that there's a fast range retreat, and there are multiple polarity reversals in the subduction, of the subductions. And then if we look at the surface kinematics, so here you have the velocity field and the velocity directions in white. And you can see that you have sometimes very, very fast velocities at the surface. And a lot of small plates that can arise and interact with each other and can rotate. And this can be assimilated to what we call a global plate reorganization event. And actually that reminded us of a specific subduction that happened in the late Cretaceous, and which we can see some evidence here at the suture zone here, which is in pink, of the Neothetis subduction. And so we'll have a look at this. Oops. Yes. At this area, so you can see that in plate reconstructions, you have this very large subduction, which is intraoceanic, and it's actually very difficult to understand how it was created. And if we look at geological evidence here, we see that actually there are some OIB signatures in the ophiolites that are now in the suture zone, and that the metamorphic soil recalled very high temperature. So the metamorphic soil can record the conditions, the thermodynamic conditions of the formation of the subduction, the Neothetis subduction. And in this area as well, what we have is that we have some evidence of magmatism with geochemical similarities with the Rhénian hotspot. So some people have argued that this is what we call the pre-Deccan plume, so before the Rhénian plume and the Deccan traps. And in this area, which is quite interesting as well, is that you have a large plate acceleration, plate reorganization, fast trench retreats, diachronous subduction, so which means the deactivation of subduction zones along continental margin. And this allowed us to by comparing our models with these observations, to propose a scenario with an induced subduction by the proto-Deccan plume or the Rhénian plume, which kind of promoted this kind of evolution and global plate reorganization in this area here. So I hope that with this kind of small overview of our models, I convinced you that it's actually interesting sometimes to look at mantle plumes in their environment, and both lithosphere and mantle heterogeneities. And just to finish, I wanted to say that something that's quite interesting next is to have a look at at how we can maybe more detect a little bit with more precision mantle plumes. And this is actually a technique that Christine has presented. So the polarity, the reflection polarities, and it's been used by Laura Cobden and her team in order to, in synthetic models of single plumes, in order to try to detect mantle plumes or not in a mantle. And so something that's quite exciting is to try to guess what would be the signal of maybe these complex structures. So thank you.
Thank you very much, Maelis.